Hello and welcome to my talk. My name is Erik Paul. I am from the University in Leipzig, and in my research I focus on max plus automata. In this video I want to introduce a recent result of mine to you, namely the decidability of the finite sequentiality problem of finitely ambiguous max plus tree automata. I will not go into any proof details and instead only show you how this problem can be decided. We will still need several steps to get there, and we'll start by having a look at what max plus automata are. So, I assume that everyone is familiar with finite automata. A finite automaton has finitely many states, and we want to accept or reject words over a finite alphabet. Every run of a finite automaton starts in some initial state. With every letter of the word, we go from one state to the next, and in the end, we hopefully arrive at a final state and accept our word. For a max plus automaton, all we do is we add weights. Weights from the real numbers all the way to minus infinity. We add one weight to every transition, and we add an initial and a final weight to every state. With these weights, we can then define weights of runs. And the weight of a run is simply the initial weight of the first state in the run, plus the weights of all the transitions which constitute the run, plus the final weight of the last state in the run. So this plus here is the plus from max plus, and the maximum comes in when we take a look at the weight of a word. A max plus automaton assigns a weight to every word by taking the maximum of the weights of all the runs on that word. The way I usually like to think of these weights is as profits. Along a run, we accumulate a profit, and in the end, we are interested in what is the maximum profit we can get with our word. What you can see here is if one of the weights in a run is minus infinity, then the weight of the whole run is going to be minus infinity. So this run will not contribute at all to the weight of the word. In this sense, the weight minus infinity marks invalid transitions or non-initial, non-final states. Let's have a look at a very simple example. This automaton here has only two states, and the alphabet is just A, B. Every run of this automaton has to start in the left state with an initial weight of 0, and it has to end in the right state with a final weight of 0. When we start a run in the left state, we can loop A's and B's, and here A gives us a profit of 1, but B doesn't give us any profit. At some arbitrary point in the word, we can decide to go from the left to the right state, and here again we can freely loop A's and B's. However, in this right state, the situation for the profits is reversed. So here, A doesn't give us any profit, but B gives us a profit of 1. Now for every word, there's going to be at least one optimal position to go from the left to the right state. So optimal in the sense that we maximize the profit we get from first taking profits only for A's and then taking profits only for B's. And this maximum profit is exactly what the automaton assigns to the whole word. Okay, a very important concept for this talk is the ambiguity of a max plus automaton. The first type of ambiguity we want to consider here is that of sequential or deterministic automata. And this is just what you would expect. We call a max plus automaton sequential or deterministic if there is at most one initial state, so at most one state with an initial weight that is not minus infinity, and there should be no two valid transitions like this. So if we are in a state P and we read a letter A, then there is at most one state which we can go to with a weight that is not minus infinity. For the other type of ambiguity, we consider the number of runs that we have on each word. So this set here contains all runs on the word W whose weight is not minus infinity, so which are valid. Then we call an automaton unambiguous if on every word there is at most one valid run. A prominent open problem about max plus automata is the sequentiality problem, the problem of deciding whether a given max plus automaton can be determinized. So more precisely, the sequentiality problem asks, given an arbitrary max plus automaton A, does there exist a deterministic max plus automaton with the same behavior as A, so which assigns the same weight to every word as A does? Now, in general, this problem is still open, but some restrictions of the problem have been shown to be decidable. For example, this problem is known to be decidable for unambiguous automata. So, given an unambiguous max plus automaton, we can decide whether this automaton can be determinized or not. This is a result due to Mori, and since we will need the result in a little bit more detail, we are going to have a look at how the sequentiality problem can be decided for unambiguous max plus automata. First, let us consider this automaton. So this is one automaton with 4 states, and the only letter we can read is A. So what does this automaton do? In the left part here, we can read all words of odd length. We start in this initial state, and after reading an odd number of A's, we end up in this final state. And the weight we assign to words we read by using these states is always 0, because we have a profit of 0 for every transition, and as the initial weight here and as the final weight here. In this right part, on the other hand, we can read all words of even length. We start in this initial state, and after reading an even number of A's, we end up in this state again, which is also final. The weight we assign to words read in this part of the automaton is exactly the length of the word. We start with an initial weight of 0, and then for every A we read, we get a profit of 1, and then we have a final weight of 0. So this automaton assigns 0 to every word of odd length, and it assigns the length of the word to every word of even length. So this automaton is unambiguous. Every word of odd length has to be read in this part of the automaton, and every word of even length has to be read in this part of the automaton. So for every word, there's at most one valid run. However, we have 2 initial states, so clearly this automaton is not deterministic. In fact, this automaton cannot even be determinized, and we'll have a look at why this is the case. Assume we have some max plus automaton A and 2 states P and Q of this automaton. Then we call these 2 states rivals if there exist words U and V which satisfy the following. First, U should be able to reach both P and Q. So by starting in some initial state and using only valid transitions, we should be able to end up in P, and the same should be true for Q. With the word V, on the other hand, we should be able to loop both in P and in Q, but the weights for these loops should differ. If we have 2 words, U and V, which satisfy this, we call P and Q rivals. In this automaton here, the 2 initial states are rivals. For U, we simply choose epsilon, the empty word. As these 2 states are initial, we can simply reach them by reading nothing. For V, we choose AA. When starting in P, we can read 2 A's to end up in P again with a weight of 0. And likewise, by starting in Q, we can read 2 A's to end up in Q again. And here the weight of this loop is 2. So we can loop in both states with the word AA, but the weights for these loops differ. Here it's 0, and here it's 2. Mori's theorem now tells us that if we have an unambiguous max plus automaton, and we do have an unambiguous max plus automaton here, then this automaton can be determinized if and only if there are no rivals in this automaton. We have 2 rivals here, so this automaton cannot be determinized. Alright, the problem which we want to consider in the following is the finite sequentiality problem, and this is a relaxation of the sequentiality problem. So here the question is as follows. Given an arbitrary max plus automaton A, do there exist finitely many deterministic max plus automata whose pointwise maximum is equivalent to A? So instead of asking for one deterministic automaton, like for the sequentiality problem, here we allow multiple deterministic automata, and then we want their pointwise maximum to be equivalent to the original automaton. Like for the sequentiality problem, the decidability of this problem in general is still open. But again, for unambiguous automata, this problem is decidable. This is a result due to Bala and Koninsky. Given an unambiguous max plus automaton, we can decide whether or not it can be represented as a finite maximum of deterministic max plus automata. Let's consider the automaton from the last slide again. We've seen that this automaton is unambiguous and that it cannot be determinized. However, if we take this left part as one automaton and this right part as another automaton, then these two automata are deterministic. And the pointwise maximum of these two automata is equivalent to the whole automaton. So the behavior of this automaton is finitely sequential. This means in particular that rivals are not a problem for finite sequentiality of unambiguous max plus automata. But rivals still play an important role, namely in the concept of a fork. For two rivals P and Q, we call a word F a fork if we can use F both to loop in P and also to go from P to Q. The theorem of Bala and Koninsky now tells us that if we have an unambiguous max plus automaton, then its behavior is finitely sequential if and only if there are no forks in the automaton. So, for sequentiality, rivals are a problem. For finite sequentiality, forks are a problem. To illustrate all of this, let's have a look at this automaton. First, this automaton is unambiguous. Every run has to start in the left state, and it has to end in the right state. So we have to take this transition from left to right at some point. Now, in this state, we can only read B's, and this transition is labeled by an A. So necessarily, we have to take this transition at the last A of the word. Every letter before the last A has to be read by looping in P, and all the B's after the last A have to be read by looping in Q. Next, the states P and Q are also rivals. For U, we simply choose A, we start in P, and we use an A to loop in P, and thereby we reach P. Or we start in P, and we use A to reach Q. So the word A reaches both P and Q. Also clearly, with B we can loop both in P and in Q, and the weights for these loops differ. Here it's 1, here it's -1. So P and Q are rivals. Finally, we also have a fork. The word A can both loop in P, and we can also go from P to Q using A. So we have a fork here. This means that by the theorem of Bala and Koninsky, this automaton is not equivalent to a finite maximum of deterministic automata. So this is a purely formal reasoning, but I would also like to give some intuition here. Recall that this transition here always has to be taken at the last A of every word. This means that every B before the last A gives us a profit of 1, and every B after the last A gives us a profit of -1. So therefore, we have to treat the B's before the last A differently from the B's after the last A. Now, one deterministic automaton clearly cannot correctly guess the last A in a word, and therefore cannot simulate the behavior of this automaton. But since we may have arbitrarily many A's in a word, even finitely many deterministic automata are not powerful enough to model this behavior. Until now, we have only considered unambiguous max plus automata, so where on every word there's at most one valid run. In the following, we want to consider finitely ambiguous automata. And here we require that there is some constant m, such that on every word there are at most m runs. So we allow more than one run on a given word, but this number still has to be bounded by a constant. And for these automata, we now again ask the finite sequentiality problem. Given a finitely ambiguous max plus automaton, is this automaton equivalent to a finite maximum of deterministic max plus automata? Let's have one more look at the automaton from the last slide. We've seen that this automaton is unambiguous and that its behavior is not finitely sequential. But let's add a new state with transitions like this. This automaton is not unambiguous anymore. Every word which contains at least one A will have one run in this part of the automaton and one run in this part of the automaton. But clearly the automaton is finitely ambiguous because on every word there are at most two runs, one here and one here. The weight of this run here, however, is always going to be smaller than the weight of this run here. So these states now do not contribute anything at all to the weight of a word. So this whole automaton is in fact equivalent to just this part, which in itself is deterministic. So by adding this one state, we've created an automaton which has two rivals and a fork, but whose behavior is still determinizable. So in particular, its behavior is finitely sequential. This means that for finitely ambiguous automata, neither rivals nor forks are a problem when it comes to finite sequentiality. So then, how can we decide finite sequentiality of finitely ambiguous max plus automata? For that, let me recall you one theorem, namely that every finitely ambiguous max plus automaton can be decomposed into finitely many unambiguous max plus automata. This result by now has several proofs. A very well-known one is by Kliman, Lombardi, Meres, and Prieur. Given a finitely ambiguous max plus automaton, we can always construct finitely many unambiguous max plus automata whose pointwise maximum is equivalent to the original automaton. Note that these automata are unambiguous, not deterministic. So let's assume that we have a finitely ambiguous max plus automaton and such a decomposition into unambiguous max plus automata. Then a theorem by Bala tells us that the behavior of this finitely ambiguous max plus automaton is finitely sequential if and only if this condition on the right is satisfied. So what does this condition on the right say? There should be a constant c, a bound, such that for every word, one of these automata, so there exists an I, one of the automata from this unambiguous decomposition, assigns a weight to the word, which is close to the weight which A assigns to this word, and close here means that the distance is not larger than C. And furthermore, on the run of this automaton, there should be no fork. So we should not go from a rival P to a rival Q using a fork. If we say that runs where we have no fork are good runs, then this condition here says we should be able to approximate our original automaton by using only good runs of the automata from the unambiguous decomposition. I want to point out that this decomposition into unambiguous automata is not unique, but it does not matter which decomposition we choose. For the remainder of this talk, we want to consider this theorem, but for tree automata. Everything I've told you so far concerned only max plus word automata. Max plus word automata like I introduced them on the first slide. Now we want to take all of this to trees. So this is the kind of tree we want to consider. We assume that we have a ranked alphabet. For example, in this tree here, every A has 2 children and B is always a leaf. A max plus tree automaton then has finitely many states, and a run of such an automaton on a tree is simply an assignment of nodes to states. So we take a tree, we put a state on every node of the tree, and this is what we call a run. Such a run gives us a transition for every node of the tree. And this transition always consists of the states at the child nodes, the transition ladder itself, and the state at this node. So for example, at this red A here, the transition at this A consists of these two states at the child nodes, this transition letter A, and this state at this node. So formally, such a transition is a tuple like this. A max plus automaton then assigns a weight to every such transition, and it assigns a final weight to every state. The weight of a run then is simply the sum of the weights of all the transitions in the run plus the final weight of the state at the root. So we look at every node, take the transition at this node, sum up the weights of all these transitions, and in the end at the final weight of the state at the root. The weight of a tree then, like for max plus word automata, is simply the maximum over all runs on this tree. Since we want to talk about deterministic max plus tree automata, it's important to note that our concept of determinism here is bottom-up determinism. So given the child states of a transition and the transition letter, there's at most one state which we can go to with a weight that is not minus infinity. We now want to consider the finite sequentiality problem for max plus tree automata. So is our max plus tree automaton equivalent to a finite maximum of deterministic automata? And for this, we'll first have a look at how all the concepts we introduced on words translate to trees. We now call two states rivals if the following holds. First, there should exist a tree U, which reaches both P and Q. And reach now means that on U, we have some run where all these transitions are valid and P is at the root, or Q is at the root. Furthermore, there has to exist a context V, which can loop both in P and in Q, but with different weights. And a context is simply a tree where one of the leaves is replaced by a special context symbol. And looping in P, for example, then means that on this tree, we have some run where all the transitions are valid. We ignore the transition at this context symbol. And at this context symbol, as well as at the root, we want to have the state P. So we call P and Q rivals if they can both be reached by the same tree U, and we can loop in both states with the same context V, but the weights of these loops are different. We call a context F a fork if there exist two rivals P and Q, such that F can both loop in P and also go from P to Q in a bottom-up fashion. And then we have one new concept, namely that of a split. And a split simply means that we have a tree with a run where all transitions are valid, and two rivals P and Q occur in different subtrees, so they are not above or below each other. For example, here the state P occurs in this left subtree, and the state Q occurs in this right subtree. The final ingredient we need is that, like for max plus word automata, every finitely ambiguous max plus tree automaton can be decomposed into a finite maximum of unambiguous max plus tree automata. So let's assume that we have a finitely ambiguous max plus tree automaton and such a decomposition into unambiguous max plus tree automata. Then the new result I want to present in this talk is the following. The behavior of our finitely ambiguous max plus tree automaton is finitely sequential if and only if this condition on the right is satisfied. And this condition looks very much like the one we had for words. So there must exist a constant, a bound C, such that for every tree there exists an index I, one of these unambiguous automata, assigns a weight to this tree, which is close to the weight which A assigns to this tree. And close here means that the difference is not greater than this bound C. And furthermore, on the run of this unambiguous automaton, there should be no fork and no split. So we should not go from a rival P to a rival Q using a fork, and no two rivals should occur in different subtrees. So if now we say that a run is good if there are no forks and no splits on this run, then this condition says that our automaton should be approximated by good runs of these unambiguous automata. Just by looking at the theorem, it may not seem that much changes when going from words to trees. But we do need quite a few new ideas to show that this condition is decidable and that it is also necessary and sufficient for finite sequentiality of finitely ambiguous max plus tree automata. Unfortunately, time is insufficient to go into any detail here, so I'll just thank you for your attention and I hope you liked the video.